Okay, so welcome everybody. In today's research seminar, we have Ilija Bogunovic, who is assistant professor or lecturer at the University College London in electrical engineering department. I'm sure you all know quite a few of his work from Bayesian optimization side of things. Previously he was a postdoc at Andreas Krause group in Zurich, where this is where I started following his work a lot. Well, I'm sure we'll hear from him some interesting stuff. I won't take more time from him. Ilija, feel free to start.
All right, thank you. Thank you so much for the invitation and great pronunciation of my name. So thank you. All right, so once again, hello everybody. And I'd like to actually, so the title of the talk is From Data to Confident Decisions. I'd like to start this talk by telling you a short story. Actually, I'd like to tell you about the procedure or the algorithm or the method that's been used for 500 years in the past. And this is about actually electing a duke or a douche of Venice in 13th century. So basically, I want to illustrate how the search procedure can be very complicated. So here the idea is that they have the electing procedure, and the goal is to find a good, smart douche, and also the one that's kind of robust with respect to the influence of the great families of Venice back in the days. So this is how they would do it, right? They would first find 30 random people from those influential families, right? So they would draw a lottery to select them. And then these 30 guys would then pretty much vote for another 9, right? So these 30 would get reduced to 9. And then the 9 of them would then elect 40 other candidates. 40 other candidates would then get reduced to 12 candidates by a lottery. 12 would choose 25, 25 would get reduced to 9, 9 would choose 45. And the process would kind of repeat until the very end, where they end up with 41 candidates. They do some interviews and then they vote for it to elect a douche. The douche is one who gets 26 votes or something like that, right? But if you think about it, this is a very, very complicated procedure that's very expensive, right? It's a search procedure that takes so much time, right? Again, the idea is to come up and to distill or to discover the best douche out there, right? That's also robust with respect to the influence of the great families. And if you think about it here, for example, and this is going to be very interesting for us later on during the talk, if you think about the first state, the initial state, the first 30 people that were chosen, they're chosen by a lottery. So it means also the initial state is kind of random. All right, and now, moving fast forward, right? Nowadays, we're also looking to solve these complex problems. We want to kind of search through vast and complex spaces to find, for example, best performing drugs or best performing materials. Or for example, in fusion research, we might want to figure out a control policy that will kind of control the coils of this device called tokamak and would enable nuclear fusion. And again, in all these applications, we again have this idea that the search space is vast, and we would like to quickly navigate through this search space to discover the best performing solutions. So how do we do that in machine learning? How do we try to automatize this decision-making process? Well, typically, as you all aware about it, right? We take our collected data and we impose some sort of a probabilistic model, and we define what we want, right? What we seek, what our optimization goal is, and based on these two jointly, right? The goal metric that we care about, and also the probabilistic model. we implement some sort of a decision-making rule, right? We plan which labels or actions to take, which experiments to run, and etc. And then we interact with the environment, which can be like a complex simulator or just humans, eliciting knowledge from humans, or other kinds of expensive experiments that we might want to run. So finally, once we get the observations, right, we take those observations, we propagate them back to our machine learning model, we update our hypothesis space over the models, plausible models, and then we repeat this procedure, right? So this is typically like a pipeline of how we automatize this search procedure in machine learning and Bayesian optimization and other types of sequential decision-making problems. Now, the two key the key themes that I'm interested in and that I'll be talking about in this problem is how do we equip this process with robustness guarantees. So in particular, I mentioned this machine on the left-hand side, which is a tokamak, which is like a machine that's produced to contain nuclear plasma. And you can think about that these machines actually, they heat up plasma up to the temperatures of the sun. So of course, this plasma cannot touch the walls of this machine, right? So it kind of levitates in the space, and you can think about it that very often we don't have access to kind of tune a lot of parameters of these machines that include like voltages, gas pumps, magnetic coils, positions, and so on and so forth, right? But we actually interact with very expensive simulator, right? And then we often want to transfer our found solution to the reality. And now the question there is, how can we design robust and reliable solutions, right? How do we search for such solutions, right? Back to our introductory story about putting a douche, right? We want to find a douche that's kind of robust with respect to the influence of these, influential families. So various different aspects that one can look for, right, when it comes to robustness in decision-making and interactive learning includes like sim-to-real gap, distributional shifts, time variations, safe exploration, all kinds of risk measurements, heteroscedastic noise, and many others, right? The main question is how do we equip our algorithms with these types of notions? And another question that I'm very much interested in is regarding data efficiency. So in particular, right, how do we minimize the number of interactions with these complex simulators? One thing that we can do, we could try to exploit the existing structure in the real world problems, right? Very often similar decisions have similar preferences, performances, and then sometimes also there might be underlying symmetries, right, in our objectives that we might want to exploit, right? So the general question is, right, how do we exploit this regularity and how do we come up with the sample efficient algorithms? And so these are the two questions that going to underline my today's talk. Now, of course, like one potential way of talking about this is through the lens of black box optimization. I'm pretty sure that all of you are familiar with this slide in particular, right? So just let me just mention it for the sake of it, right? So the idea is that you have some sort of a black box, and you'd like to collect points xt, right? You want to make the decisions xt. And then you receive the noisy observation of this black box, you augment your data set, right? And then this process typically repeats. Now in Bayesian optimization, we typically place some sort of prior over the unknown objective, right? And then by using our data that we sequentially observe, we are able to kind of update our prior to our posterior, right? And to kind of learn about the underlying objective. While simultaneously, right, our goal is to optimize this objective, maybe finding the best performing point in our design space that maximizes this unknown objective, right? Now, over the course of a couple of decades, various different acquisition functions that tell you how you should be picking these XTs at every time step have been developed. Just to mention some of them, Thompson sampling, probability of improvement, expected improvement, GPU-CB, and many others. To be able to talk about this model-based approach to say black box optimization, right? A very useful tool that I'm going to be using today is the one of model-based confidence bounds. So here the idea is that you want to fit a Gaussian process or like a kernel ridge regression to whatever data you have collected so far. And then basically the idea is that you want to build the confidence intervals around it based on the collected data. In particular, saying that for each point in your design space and at every time step, the true function that you're optimizing, this denoted as f here, belongs to the confidence intervals, which is just the posterior mean plus minus the scaled posterior standard deviation. And yeah, so this is basically something that we can do in the closed form for, say, Gaussian process models. In particular, for this to hold, right? We need to appropriately set this beta parameter, right, such that the function is contained within the confidence intervals. So this beta typically depends on the complexity of the underlying function f. It also depends on the noise model in the observation process, but it also depends on the model capacity, right, which is a kernel dependent quantity, right, depending on the underlying space of functions that we work with, right? We might need to use a different quantity, this gamma k, which is maximum information gain. So it simply tells us what's the maximum information that we can extract from the prior by querying the unknown function at, say, capital T or T in this case locations. So it's has this nutshell notion of diminishing returns property. And yeah, like we know the upper bounds for this quantity for various different kernels, including, say, a matern kernel, family of matern kernels, squared exponential kernels, neural function kernel, and others. All right, sounds good. So this is going to be very relevant for our upcoming slides. Now we can also define the upper confidence bound, right? Which is, again, I already mentioned it. It's just simply the posterior mean plus the scaled standard deviation. So here in this picture, it's given as the upper gray curve, and the lower confidence bound that we denote with LCB is just given as the lower curve in this figure. Now, one of the famous algorithms out there that has favorable regret guarantees is called GPU-CB, upper confidence bound. So it just amounts to playing according to the maximum of this upper confidence bounds, right? So if you're just to run this for a couple of iterations, you can see that this particular algorithm that always queries the maximum upper confidence bound kind of converges to the maximum of the function. So yeah, that's pretty much like the background. And it turns out that in some other situations, for example, when we have a model misspecification, or when our observations go beyond just the sub-Gaussian noise and can also be adversarial, we can actually construct similar confidence intervals, and we've shown some of this in our previous works. So in a sense that these tools are more widely applicable to other settings as well. All right, now we have our model, right? And we have our protocol where at every time step we query XT, and we get to see a noisy observation. One more thing that we haven't talked about are the different objectives that we can look for, right? For example, optimization is one of them. We mentioned this, but we can also look at, say, the level set estimation problem, where we try to discover all the designs in the input space for which the function is above a certain threshold, or we might care about the estimation problem from noisy observations, or just we might want to track a function over time as it might be changing over time. And there are all other robust aspects this optimization process that we might look for, such as minimax and risk-averse objectives. We can also pose the games with unknown objectives, distributional robustness aspects, and many others. So we'll touch base on some of these by the end of this talk. All right, so I'd like to start by introducing this robust Bayesian optimization. So all the previously constructed Bayesian optimization methods that I've shown on one of the slides, they kind of ignore the robustness aspects, right? So what do I mean by this? So imagine here that we have some unknown function f that is a function of two variables, x and c. So x is a decision variable and c is some sort of a contextual variable, right? So your function depends on both of them. So for example, x can be, the height of your air turbine, and c can be, for example, weather conditions out there, right? And then f could be, for example, the amount of power being generated. So that could be one problem, right? And now what we want to say, we consider the following scenario where we have access to some expensive simulator, right? It might be very expensive to create the simulator. For example, in this particular problem, getting some sort of next state predictions of the plasma state inside the tokamak amounts to solving, complex physics equations, and sometimes, the obtaining even a single observation can take hours, right? So we would like to minimize the number of interactions with those expensive simulators. So here we assume that we can actually query the simulator both at the decision and the contextual variable, right? So we can simulate the conditions inside the, say, this particular machine, right? And then we receive a noisy observation from the simulator, and then we play this game for, say, capital T rounds, right? And after that, we just want to recommend the single point, x capital T, right? So now we take this single decision that we have, and then we transfer with it to the reality, right? To the real thing, right? So we actually implement this final decision that we discovered on the simulator, right? So that's the idea. So how do we find a robust x hat T, right? That's going to work well across different contextual variables C, right? That can happen at the test time, right? Once we go to the reality, right? So that's the main question. So, if the function was to be known, like this would be a very natural problem. You just, do a minimax, right? Actually, in this case, because we're working with the rewards, it's a maximin, right? But of course, the function is unknown. So we need to figure out a way to carefully sample this function, right? So the first idea that one can think about is just, hey, let's replace this unknown function with its upper confidence bound, right? So let's be optimistic about it. Right, so this is similar to the classical UCB algorithm that you've seen, but now it's a max-min. And then basically, so yes, please go ahead. There's a question.
Yeah, sorry, just one clarification point. So this is assuming that your goal is to give you the best performance under the worst conditions.
Exactly. Yeah.
Cool.
Yeah, that's the.
It's not like best average or something. It's like best under the worst. Yeah.
It's just best in the worst case, right? That's why it's kind of the robust optimization approach, right?
Yeah, cool. Makes sense. Thanks.
Yeah, thanks for the question. All right, so now that we have this xt, right? So we might decide now to query the function at point xt, but it turns out this is not enough. And this is not sufficient to provide you a non-vanishing regret guarantees. So the next thing that we need to do here, we actually need to take the previously found xt, and we need to find the worst condition for this particular xt. But because the true function is unknown, right, we either need to use a posterior mean or UCB or LCB, but it turns out that here you need to be pessimistic about it, right? So you need to use the lower confidence bound here. So pretty much the idea is that not only that you're looking for the worst condition, but you also need to be pessimistic about it if you want to figure out the worst case, given that the function is unknown. And now we have the pair xt-ct, and we can just query the unknown function at this pair xt, ct to get the observation. So I'm not going to go into detail, and I know that it's kind of hard to see this, even for me, But what's happening under the hood is that this type of search procedure, exploration procedure, actually eliminates parts of the space, for which the worst case UCB is greater or equal than the best worst case LCB. I know it sounds incomprehensible, but just intuitively, it kind of shrinks down the space where the max mean optimal point cannot be, right? So it kind of discards it. So that's what is going on. All right, and for this particular rule, right, we can also show the required guarantees or the optimality guarantees. So in particular, here we are calling our algorithm stable opt, so it combines pessimism with optimism to find the max mean point, and or max mean design, right? And here we are pretty much specifying the number of samples denoted as capital T. That we need to execute, right? That we need to sample before we're sure to output an epsilon optimal minimax point, right? Minimax solution. So here, the number of time steps or the number of samples that we need, it depends on the width of the confidence intervals. It depends on this maximum information gain, which is a kernel dependent quantity, telling us what kinds of function class we're working with, and it also depends on the precision epsilon, right? So the more precise solution we want, we need to pay more in terms of samples. Of course, now we can replace the bounds for this maximum information gain to actually get the proper upper bounds on the time step for different kernels. For example, here I present one for the squared exponential kernel. You can see here, for example, that still the number of samples is exponential in D, of course, right? We cannot avoid the curse of dimensionality, but at least, right, the smoothness of the squared exponential kernel allows us only to have log 1 over epsilon to the D, right? So the smoothness is fighting the curse of dimensionality for these well-behaved kernels. And I can also tell you, right? So these are the sample complexity guarantees in the worst case. And I can also tell you that we also have the lower bounds for this problem, and our lower bounds are neither matching the upper bounds. Yeah. I think I won't be going into details of the proof. In principle, like all the steps of the algorithm plus some sort of a reporting rule is necessary to get the previous results. So maybe if time remains, we can discuss it briefly. So what we did, right? We also looked at the same problem in the domain of reinforcement learning, where we just replaced the designs, right? The point X with the policies. So we just implemented the same algorithm in the policy space, and then we tried it for the robust RL objective. So this was done with Sebastian. So in particular, we now have our algorithm that's called RHUCRL, which is pretty much the RL version of stable opt, if you want to think about it like that. And here we look at the worst case return in Mujoko environments. We have 6 different Mujoko environments. So here the idea is that you have the learner's policy that tries, these agents are trying to learn to walk, right, to cross the distance. While at the same time, there's an adversary that applies certain force to their joints, making it harder for them to walk, right? And pretty much now we implement this stable opt type of algorithm to find a robust policy. And now we look at the worst case return here. So we compare against robust heuristics. We compare against non-robust model-based reinforcement learning, and we compare against deep robust RL, which is a model-free algorithms. So these algorithms, they take 5 times more samples than we do to find a robust policy. And you can see here in the first plot, our algorithm achieves the highest worst case performance. And pretty much this happens everywhere in all these environments. Even if you look at the average case performance, it turns out that this type of adversarial training that we apply here kind of helps, because sometimes we actually even have the highest average performance amongst all the algorithms. So I think the main message here is that this type of this type of exploration that we apply is sample efficient, and we managed to discover robust policies for these environments. All right, another idea that I'd like to tell you about, which is also kind of related to some notions of robustness in decision-making algorithms, is the following. So pretty much we again look at this generative model where we have access to a simulator, right? And we can query the simulator at any state action space, for any state and for any action. And our goal is to identify a near optimal policy to control this system. One thing that we're looking, so this is kind of pretty much related to all kinds of simulators, including self-driving simulators, plasma control and those types of simulators, also in robotics and so on. In all these cases, samples are expensive, right? And we would like to identify policy in a sample efficient way. Now, one twist that we look at here, right? This is also known as the RL with the generative model, is the following, right? So if you look at these chess boards in the right-hand side corner, so basically what's happening here, you can see that the second row in these chess games is randomly permuted. So this was a game called Random Fisher. This is the photo of Bobby Fischer, a former world champion in chess. So he proposed a game where the idea is to change the initial state of the game, right? To kind of randomly permute the second row. So the idea is that you want to strip the grandmasters of their book knowledge, right? And have like a more fun way to play the chess game, right? Now, if you think about the grandmaster as an expert policy, right? If you kind of permute the second row, then they might no longer be behaving as experts, right? It's going to be harder for them, right? For sure. So the idea here is that we would like to discover policies that are robust with respect to the different initial states that they might encounter. Again, if you think about this fusion application, once this nuclear plasma forms inside those tokamak machines, we don't know the prior states. Like we don't know the initial state, how the plasma forms inside those machines, right? So this is one of the ideas. So how can we tackle this particular problem? Let's first try to formalize it, right? And I'm going to use just the episodic Markov decision process, just the standard definition. So we have a set of states, set of actions, and then the policies being executed for capital H time steps. And we have some sort of a reward function. So the agent at every time step within every episode, it selects state and action to query the simulator. And then the simulator transitions to a new state, and the agent also gets to observe the new state plus the reward. So this is what it means to have the generative model, access to the generative model or the simulator. And we can, of course, define the standard definitions of the value function and the Q function, right? It's just the expected sum of the rewards given the state in case of the value function, and the expected sum of the rewards given the state and action for the Q function. All right, so this is our objective, right? So we want to play this game of sampling for, say, capital T runs. And after that, we just want to output a single policy that is robust, that is robust with respect to the initial state. So that's why we care about the infinity norm here, and we want the value function of our reported policy to be epsilon far from the optimal one for any state. So that's the objective. All right, so the idea is pretty much similar to the one that I've shown you, right? So what we are going to do, we're going to assume certain regularity assumptions on the reward and Q function, in particular that they can be modeled by using some kernel, right? And then what we're going to do, we're just going to apply the kernel ridge regression to come up with the estimate of the Q function. So that's pretty much the idea. And then we're going to come up with the estimate the uncertainty by using the following term that's pretty much in terms of Gaussian processes, we are talking about the posterior standard deviation, right? Okay. So that's the learning algorithm. So this is kind of shown here, right, where we have the Q star, which is a true unknown Q function, and then we have our estimate at time t, right, which is given as the Q hat, right? Now the idea is, again, we can obtain the upper and lower confidence bounds for this, that we denote as the upper, the Q underbar and Q upper bar, right? So these are our estimates, learned estimates of the upper and lower confidence bounds at time step t. And yeah, so that's the learning procedure. Now the idea is how shall we query the unknown system to discover such policies that are robust with respect to the initial state. We perform here active exploration, and how do we do that? So the first is a very simple idea. We know that the optimal policy is greedy with respect to the Q function. So that's pretty much by the definition, which means that we only need to learn Q star, right? At each state, we only need to learn about the best action. We don't need to learn it kind of everywhere, but we need really to focus on the best action per every state. So that's the main observation. And so this can be shown, by this simple picture here, right? So we want to query the state that is most uncertain regarding what's the optimal action for my agent in that state. So that's the idea. That's pretty much where I need to obtain more knowledge about the Q function.
Okay, sorry, can you remind us like what are the assumptions of the size of the state space?
Sure.
I mean, I assume that let's say that it's really large one, like, I don't know, Go game. I mean, you would end up with uncertainty everywhere.
Right. So pretty much here regarding the state space, right? So pretty much this allows you to have like a very large state space, because what we're doing here, we want to kind of similarly as in the Bayesian optimization, right? You can even have like a continuous space, right? So it does not need to be a discrete space, right? So in a sense, right, from a theoretical point of view, this also works for a very, very large state spaces. Of course, you need to be able to solve the kernel ridge regression problem, right? That's the underlying thing, right? And then again, you end up with all these problems of inverting the matrix with the number of observations. But the state space should not. The size of the state space, at least, should not be the problem.
Right.
From the computational perspective.
I think I wasn't referring to that. I was mostly more concerned about, okay, if you have really huge state space, you end up with a really large sections of space that are very uncertain. So you end up exploring for a very long time.
Yeah, sure. I mean, if you want to get these types of guarantees that work out everywhere, right, you cannot avoid that, definitely, right? So if in case that your state space is discrete, right, then basically what helps you here is that if there's a correlation between the states, right, in terms of the function values, then you can skip, visiting all of them, of course, right? But if there's none, right, in the worst case, you need to go and visit every state pretty much and get the function observation everywhere. Yeah. But again, if there's such a, if the correlation is captured well by your kernel, of course, you're going to save some number of samples.
Okay, thanks.
All right. Okay, cool. So now that we have our state that we're interested in, now we need to decide upon an action, and to realize which action we want to try out next. It's just what we rely on optimistic action, which is just the upper confidence bound of the estimate of the Q function. for this particular previously found state. So this, you can think about this, that we found the action given the state, and then we just play UCB algorithm. All right, now we gather the observation, right? And then we use it in our value iteration algorithm to update our estimates for the upper and lower confidence bounds. And pretty much this loops kind of over, right? Where we collect more and more samples. So if I'm just to summarize everything, so after capital T runs, right? The idea is that we'll be learning the optimal value function for every state. And finally, we just report a policy, which is just the one that for every state maximizes the lower confidence bound of the Q function. So yeah, that's just the reporting rule at the very end. But now I want to just summarize what we just did, right? It's super simple if you think about it. We just designed a rule how to explore state and actions at each time step. And this can be summarized into 2 lines, right? So that's the only contribution here, right? So again, I'll just try to repeat it. So in the first line, you pick a state for which you're most kind of uncertain about the optimal action. And then in the second step, you just pick the action that has the highest upper confidence bound score for this particular state. And so that's our exploration strategy. That's pretty much all. Yeah, so that's the recap of the sampling rule. Again, we can get the similar types of guarantees, right, as the ones that I've shown. So I'm not going to spend too much time here. The only difference here is that you need to account for this episodic notion of the MDPs. So we get the extra factor of that depends on age, which is the episode size. But the nice thing here is that you get these near optimal rates for best policy identification across any possible starting state. So the policy is going to be near optimal for any initial state that you might end up with. Yes, please.
Quick question about the previous slide. So you had this difference between your upper and lower confidence bounds.
Mm-hmm. Yeah.
Is the action of these two, are they both the same action? Are you looking for the highest?
No, they're different. They're different. Nothing would change even if you use the same action. In which case, that would just be uncertainty sampling, right? But this seems to be a bit tighter, and you'll see in our experiments that it works better than just uncertainty sampling.
Okay.
All right.
Okay.
Great question. Thanks. All right. So let me show you some results, right? So what we did here, we actually compared our method, which is active exploration, LSVI, so the first column, against just the random policy, then the policy that queries the simulator according to uncertainty sampling, which was just mentioned. And then we also compare against other algorithms that are online, like LSVI, UCB, double DQN, Bayesian DQN, and greedy method, right? And so what we assume in our first experiment, we assume that the initial state at the training time is the same as the one at the evaluation time, right? So there's no discrepancy in the initial state. So here we are looking at 2 environments which are related to control of nuclear plasma, magnetic coils in tokamak machines, which are kind of related to economic costs of the fusion process, and the second one are actually multi-objective. Kind of looks at this pressure in plasma plus rotations inside plasma, which are kind of correlated with whether the plasma is stable or not. And the longer you can maintain the fusion, the more energy you can get out. So that's a very vague explanation. And what we can observe pretty much is that these online algorithms, they're outperforming our algorithm. So they work better, right? And also, if we include some other well-known environments like carpool navigation, these algorithms perform better. So on the other hand, right, when we actually change the initial distribution so that it differs from the training time, then it turns out that our algorithm beats all the other methods. So it is more robust against the starting state, and we're able to get higher rewards and better policies. So that's the bottom line message here. We actually applied this same algorithm for RLHF, which is kind of popular nowadays, right? So the idea is that obtaining this preference-based feedback for fine-tuning large language models is quite expensive because it involves querying humans. So we kind of applied this algorithm to actually get, which prompts and which answers of humans we should, of LLMs we should label to collect data. And can we actually have like a good policy for active learning and active exploration in this particular case? So that's one of our newest works that I'm not going to talk much about today. Finally, we also had a recent robust extension of this problem. In particular, we looked at the distribution in robust reinforcement learning with a simulator. So the idea here, very roughly, is that we have an algorithm that interacts with the simulator to learn the transition dynamics, right? So, for example, you can use Gaussian processes to model and to learn the model of the transition dynamics. And then we use this model inside the model-free algorithms, RL algorithms, that are robust and that can also take the uncertainty set around this estimated model, right? So there might be some inherent uncertainty about the estimated model, right? For example, when transferring from sim to real. And after you do that, after you run this model-free algorithm, but now in terms of the learned model, not in terms of the actual simulator that's very expensive, right? Here the samples kind of come for free, and you can use model-free algorithms, which are known to be sample inefficient, right? Then you end up with a robust policy, and now you can take this robust policy and run it in the real world. So basically the idea of this work is to come up with a model-based approach for active exploration, to discover policies that are robust with respect to, this sim to real transfer. And we provided statistical guarantees for various uncertainty sets that you might build around your estimated model. And we've shown that actually our algorithm, if you see here the number of samples before we are able to output those near optimal policies, is of orders of magnitude with respect to other deep model-free RL methods out there. So this is also one of the recent works that we had. All right, let me see how I'm doing in terms of time. Maybe I can very quickly conclude with one more line of work, if that's fine.
Yeah, I think you have. We have 10 more minutes for sure. So
okay, I might need just 5 minutes. Just want to highlight the following thing. Right. So in many applications that we work with, right, sometimes we'll deal with outliers, or it might happen that there's some attacker or adversary that can corrupt your observations. And in that case, a lot of these algorithms for Bayesian optimization or kernelized bandits or whatever one calls them, right? They might be very fragile, right? Just here's an example, right? You have some function given in blue, and you have some global maximizer and the local one, right? And imagine that there's an adversary that corrupts in the region, that corrupts your samples in the region of the global maximizer. It means that it just injects some adversarial poisoning. So if there's an adversary, and if it just injects like some additional adversarial noise, right, inside your observations, in only 2 or 3 observations, right, what can happen is that if you were to run just standard Bayesian optimization algorithms, say GPU-CB, it would just converge to the local maximizer. It would just eliminate this piece of region, saying, hey, this is not where the optimal point is. And it will just incur the linear cumulative regret. So it's very easy. It's very easy to omit the optimal region in this case. And of course, like a very simple fix is to enlarge the confidence intervals, right? So if you're going to use the corrupted mean estimator, the corrupted posterior mean, right? Then basically you need to account for the bias that's being introduced. So what we need to do, we just need to take the simple UCB algorithm, right? We use the corrupted posterior mean that's computed based on the corrupted observations. And then we take the standard confidence interval length, which is here beta t in green. And in particular now, what we want to do, we want to kind of enlarge it by this amount, capital C, which is simply the total amount of corruption being injected in the system. So that's the simplest idea, right? You need to make your confidence intervals more robust. And now if you're to run the previous example, even if the adversary is playing you out and corrupting samples in this optimal region for some time until it exhausts its budget, right? You can still be robust and converge and recover later on and converge to the optimal solution. All right, so in terms of the, go ahead, please.
So those that total corruption,
yeah,
C. So that's something that you have to assume as a prior.
Yeah,
it's not learned. Right?
So for this UCB type of algorithm, you kind of need to assume that it's kind of given to you, at least its upper bound, right? You don't need to know it exactly. You just need to know the upper bound. But I can tell you that in subsequent works that I had in this topic, we actually relaxed this. So we provided a new algorithm based on phased elimination that does not require any knowledge about C. Right? So, and basically that algorithm actually achieves best of both worlds, right? If there's no corruption, it gets you the standard regret guarantees. But if there's corruption, it scales the guarantees scale gracefully with C. So there's a way to circumvent this. I just decided to explain the simplest algorithm out there.
Okay, so perhaps some follow-up questions. So it works. I guess it might also work. It doesn't have to be adversarial nature. It can be.
It does not need to.
Outliers in the data.
It can be outliers. It can be other type of noise that falls beyond sub-Gaussian noise as well.
Right. And you are saying that you don't need to kind of filter these observations out for training your models.
You don't, but I'm going to tell you, I'm going to conclude with basically that idea that you need to filter out if you want to get better guarantees. Yeah.
Okay.
That's going to be my punchline for sure. Okay.
Okay.
Sounds good. Very good questions. All right. So here's the guarantee of this this robust GPUCB, right? In terms of the cumulative regret, hopefully everyone's familiar with cumulative regret. So it consists of two terms. The second term corresponds to the non-corrupted regret bound. This is the regret bound of standard UCB algorithm, right? Standard Bayesian optimization cumulative regret guarantees. So here you incur an additional regret that depends on the amount of injected corruption, right? Capital C. And basically the whole analysis of this proceeds just by upper bounding the bias inside the corrupted mean estimator versus the true one, right? And basically, if you manage to upper bound here, so I'm showing this pretty much here, right? So this difference can be upper bounded by this quantity, and this quantity is pretty much the quantity that we use to enlarge the confidence intervals. So that's how we ended up with this previous slide, right? With here. How much we enlarge the confidence intervals pretty much depends on this obtained bound here. All right, but now the problem is, right? The main question is, can we do better than this, right? So if you look at the regret guarantees here, you have C multiplying square root T. So it means that we can still achieve sublinear regret guarantee if C is comparably small to square root T, right? So, C needs to be strictly smaller to scale strictly smaller than big O of square root t, right? For the regret bound to be sublinear, right? Now the question is, right, can we decouple, right? Here we have a multiplicative joint dependence on C, on the total injected corruption and square root t. But the question is, right, can we do better, right? Can we decouple them, right? And it turns out that we can, right? And this requires new ideas. So the first idea, as Ilija was mentioning, is that pretty much you need to come up with the robust estimator, robust mean estimator, instead of this corrupted one. So what we proposed in our newer work is that instead of using the corrupted mean estimator, you want to use the estimator that kind of samples this, that's based on the samples for which you have quite a few samples that correspond to the same point, right? So in a sense, you resample the same point or its region, depending on the kernel multiple times, and then you average out the observations. And that's what you use to compute your posterior mean instead, right? So this is a more robust estimator. But the problem with this is that you get a new notion, a new trade-off. And the trade-off is between robustness, right? By sampling many times at the same location, you're increasing robustness because you're becoming, the adversary needs to spend more of its budget fooling you about this particular function value. But on the other hand, you're kind of not learning much, right? If you're just sampling at the same points, right? You're not exploring, right? Your maximum information gain does not grow, right? So that's the problem, right? And you have this non-trivial trade-off that you need to balance out. And pretty much that's sort of the main idea about our new algorithm that kind of improves upon this theorem. Yeah. So that's sort of the main idea of how this problem can be tackled. So we just tested out this on a few synthetic examples. So we actually came up with certain attacks for Bayesian optimization algorithms, how you can attack them. And then you see here, for example, that GPU-CB incurs linear regret against most of the attacks, while our algorithms shown here and here, they just basically are robust and can incur the sublinear regret still, despite the attacks. All right, this is my last slide. So I want to point out that, of course, we need to be able to, in all these applications, we need to be able to estimate uncertainty, right? So that we can focus our sampling rules on what models do not know. And in that sense, right, active exploration is very important, but it's also very important to have these robust objectives in those critical applications or applications where robustness is needed. And I think both sample efficiency and robustness aspects are very important in sequential decision making. So with that, I'd like to conclude this. And so these are the main references. And this work wouldn't be possible without the amazing set of collaborators whose names hopefully I have listed all of them here. So thank you very much.
Thank you, Ilija.
Yeah, thanks a lot.
It was wonderful. I think we could see quite a few of our problems that we encounter in applied work in your problems that you have studied. Questions?
Unfortunately, I have to go, but we're catching up in 30 minutes.
Sure, sounds good. See you later.
Anybody else online?
Yeah, I've got a half-baked thought. So I guess that was focused mainly on, like an adversarial instance where you make a new measurement, adversary has to expend new budget to kind of corrupt that point. There's like, I guess sometimes we have problems with like model misspecification or I don't know, something goes wrong with the algorithms basically, and you end up computing something that isn't quite right. But maybe if you redo the calculation, you still end up with something that isn't quite right. I guess this doesn't really help in that setting, but maybe you have some thoughts about that.
Yeah, I can actually tell you that we had this work. It's called misspecified Gaussian process bandit optimization. So in that one, I haven't talked about this one, right? But we assume that basically we assume that the true function does not belong to a particular RKJS. But for example, what the underlying assumption is that there is a function that belongs to some RKJ space of the kernel that you're using that is epsilon far away in the infinity norm from the ground truth, right? And then basically the question is, what can you do then, right? So this is kind of like a misspecified problem. And it turns out that in that case, of course, your regret or sample complexity will depend on the epsilon, right? So you typically get, and this is unavoidable. So for example, if you look at the cumulative regret guarantees, you get t times epsilon, which means that your regret is linear in t, right? And depending on how epsilon scales with respect to t, you might be still able to learn and to kind of get sublinear regret guarantees. So that's, for example, one problem that we looked at. And pretty much the idea is the same, right? You need to enlarge your confidence intervals by something that depends on epsilon. So yeah, it's very similar notion. But again, you need to there are also algorithms that do not require you to know this epsilon in advance. So that can be robust even to not knowing epsilon. But yeah, that's also a good question. In that case, right, nothing is adversarial, right? There's no adversary being present, so it's a bit easier setting. Let's just call it like that.
Yeah, makes sense.
So I was wondering about your sim to real kind of approaches. When I think fusion reactor perhaps is a bit more extreme because you have only perhaps one or few chances of building a prototype. It's because it's so costly. But in other industries, perhaps, okay, you have potentially very good simulators, but not, of course, not amazing simulators. So there's always going to be some error. But you do have some prototypes and some real data that you can get and potentially inform the models that you used in simulations to kind of improve the transfer to the real world. I mean, in our case, of course, the examples are cars. You design cars, you have good simulators of a whole vehicle, and then you can explore the design space of cars using those simulators. Sure. But then once you start building prototypes based on those simulators, you might want to, after you get the real cars on the road, you start testing them, you start seeing deviations, you might want to inform the models with the real data, potentially do some further tweaking of the simulator and some further active learning on the simulator. Do you have any thoughts on that kind of scenario?
Yeah, I think that's the interesting one. I think at some point I also discussed this type of idea, right, where you have access to the simulator, but then from time to time you also get some real world data, right? And how can you incorporate that? I think it's a very natural problem and probably very, very relevant from a practical point of view. Now, again, how do you tackle this problem, right? Well, I think various variations of this problem could exist, and also depends on the amount of data that you can access from the real world versus simulator, right? But I guess, right, you can sort of try to do something like multi-fidelity type of approach, right, where the simulator is kind of less costly than the real world, right? But then again, less precise than actually rolling out the policy or the design, trying out the found design in the real world, right? And then kind of trying to kind of tackle it in such a way So that could, for example, be one potential way how these two could be combined together. But yeah, I think that's a very relevant setting that, as far as I know, I haven't seen any works that study this particular setting in this realm.
Okay, thanks. Perhaps one final question. We have a bit more time, but otherwise we would close it down. Going once, twice. Okay. Well, let's thank Ilija again for a great talk. We'll
Thank you very much.
see each other in the one-to-ones.
Thanks very
Thanks
much.
a lot.
Bye.
Cheers.
Thank you.
Bye.
Thank you for having me.